I'd like to welcome you today to the second seminar for fall for Buchanan1 F13. And today's seminar will be Travis Buchanan, and he will be talking about that. I'll let him tell you what it is.
Thank you, Dr. Luth. As Dr. Luth just said, or Dr. Luth wanted to say, the topic of my presentation is the synthesis, characterization, and application of fluorescent 2,5-bis benzoimidazole 2-eel-pyrazine dyes. So, in order to guide our conversation this morning, I've provided this overview. First, I want to discuss some relevant background material that's going to make the discussion hopefully a little bit more productive. And then I'll introduce the template molecule from which a series of derivatives will be synthesized. And then I'll actually discuss the synthesis of those derivatives and how we made these molecules, or how they made these molecules. And then I'll move on to a discussion of the various spectral characteristics of the molecules, both in terms of the fluorescent and absorption properties. And then I'll discuss how this was made into a polarity probe. And I'll introduce the details of that as necessary. And then I'll tie everything together at the very end. I don't need that. So let's begin with a review of some relevant background information. First, what we need to have a solid understanding of at least is the nature of electronic excitation. And this is obviously goes hand in hand with fluorescence, which is the absorption or the emission of light at a longer wavelength from which it was absorbed. We also need to realize that did not do what I thought it would. Okay. We also need to realize that every electronic state is actually composed of a series of vibrational states, or there are a series of vibrational states within each electronic state, and this is known as vibrational fine structure. And the transition between the vibrational states within electronic states is governed by probability. So we can see that well with some sort of diagram like this. So this is plotting energy versus nuclear coordinates. And what this blue line represents is an electronic state, the ground electronic state. And the second blue line represents the first excited electronic state. And these horizontal red lines are the vibrational states that exist within each of those electronic states. So the line I have here, labeled A, represents the absorption of an electron from the ground vibrational state of the ground electronic state to a higher energy vibrational state within the excited electronic state. Then, once that absorption has occurred, a phenomenon known as vibrational relaxation will take place, in which the electron will come to occupy lower energy vibrational states within the excited electronic state. Then, as you see F, here labeled F, fluorescence will occur, which is just the emission of that photon down to a higher energy vibrational state within the ground electronic state. It's a pain to say, but that's how it is. Now, as you see, this line I have labeled A is bigger than the line for F, which means that the energy of the emission is lower than the energy of the absorption. And that's a red shift. That's a red shift when the energy of the emission is smaller than the energy of the absorbance. Now, especially for the organic chemists, the most interesting molecules for this, or that are involved with this sort of behavior, are conjugated organic molecules. And conjugated organic molecules have a series of alternating double and single bonds. Alternating double and single bonds. And what this allows, and why it's important, is it allows all of these parallel pi orbitals to interact over the entire molecule. So we get a large track, you could think of it as, of overlapping pi orbitals, which allows the electrons to be delocalized, which means that conjugated molecules are a little bit more stable, or are more stable than non-conjugated molecules. And this also allows for some interesting energetic differences between the involved orbitals. So if you imagine that a sigma bonding orbital would be here in your molecular orbital diagram. The corresponding sigma anti-bonding orbital would be way up here, with a large energy difference between them. Now for a conjugated molecule, the HOMO and the LUMO, meaning the highest occupied molecular orbital and the lowest unoccupied molecular orbital, in a conjugated molecule is going to be much smaller, because it's going to be between a pi bonding orbital and a pi anti-bonding orbital, not those high energy sigma orbitals. And since that energy of transition is smaller, sometimes conjugated molecules can absorb light that is very close to the visible spectrum, very close to the blue end of the visible spectrum. It's still in the ultraviolet spectrum, but as we know, through vibrational relaxation, the resulting emissions might appear in the visible spectrum. which is, and that's the most dramatic example of fluorescence. You shine invisible light at something and then it starts glowing. Well, that's what's actually happening, and that's why. Now, because of the nature of conjugated molecules that I've just pointed out, these are useful and used frequently as dyes, particularly fluorescent dyes. And it's just inherent with the nature of conjugation that there are large concentrations of partially negative charge in these molecules, which is the large overlapping pi system. And what this can lead to is special interactions with solvents. And the changing of spectral characteristics based on solvent interactions is known as solvatochromism. And I'll talk about that a little bit later when I discuss the probe and how it works. So now this brings us to the molecule from which all these derivatives are going to be synthesized, which is, you can either say that or you can say BEIP, which I like more. And this is a nice molecule because it has a very large system of conjugation, conjugated all the way around, which is nice. And it also has these nitrogen atoms here that they can be functionalized. You can add things to them, which means this molecule has a lot of synthetic potential. There is a problem, however, in these molecules because all of these atoms are sp2 hybridized. This molecule is flat. And what that means is it can stack. And when it stacks, it resists solvation because it's a higher affinity for other molecules as opposed to being actually solvated. So that brings us then to what we're trying to do, or what they were trying to do. And that one of those synthetic objectives is to actually improve the solubility of BBIP. And they wanted to do that by adding alkyl substituents to those nitrogens that I pointed out and said were functionalizable. So, and that would break up the planar nature of the molecule and allow it to be solvated. They also, or we also, want to discuss the absorption and emission properties to find out what spectral characteristics these things have. That's obviously important if you want to market this as a dye of some sort. And then we want to find out how this can actually be applied. And the application they chose was a polarity probe. And the way they went about doing this was they tried to craft this dye into the backbone of a polymer. And more about that later. Now let's actually discuss the synthesis. How did they make these molecules? So, this first synthesis is how they made the initial molecule, the first derivative, which has just, as you see on your handout, it's molecule 1. So this first step is going to be that synthesis. So what they began with, or the first reaction that's interesting, is this reaction right here, and below it I have the mechanism. So they took this molecule, reacted it with butylamine, where Bu represents butyl, or that group right there, to achieve this. And I actually want to talk about the mechanism a little bit. So what we need to realize right away is that this molecule has a reactive contributing structure, which is this molecule right here, which has a positive charge adjacent to a bromine. And what that means is this lone pair on this butylamine would very much like to attack that positive charge. And it actually joins the ring here along with the bromine. So now we have this structure right here. Then, via some electronic shenanigans, the bromine is booted off, or it boots itself off, to give this molecule right here. And then that bromine, which is just floating around, can pull off this hydrogen right here, making HBr, and we have this final molecule right here, which is the same as that molecule. So that's the mechanism that gives us that. But we're not done yet. This molecule itself isn't very useful. What we need is to have a reduced form of it. So what they did was they reacted this with hydrogen gas in the presence of or hydrogen in the presence of a charcoal-activated palladium catalyst in methanol. And the mechanism for this is probably sort of complicated as redox reactions are, so I'm not going to talk about that. I can say, or I can speculate, rightfully or not, that it is probably going to involve an oxidative addition of hydrogen onto the palladium catalyst, followed by a reductive elimination of hydrogen ions onto the nitrogen to give us this. Now this molecule is actually very useful because it can be reacted with pyrazine 2,5-dicarboxylic acid. So if we take two equivalents of this, you can sort of imagine one of these molecules aligning on either end of this dicarboxylic acid, which with a dehydration reaction, which is brought about by the polyphosphoric acid that is present, or is coaxed into the forward direction by the polyphosphoric acid, which also provides the medium for this reaction, we can get this molecule right here, which is the first derivative of BBIP. And as you see, all we did was it's still BBIP, it's just got really big alkyl chains hanging off of those nitrogens. So that's the first derivative that we're interested in. Now, the second one, which you'll see is 2 on your sheet, is actually going to start with just regular old BBIP. And what we're going to add to this after we react it with sodium hydride is Bach-protected omega amino alkyl, alkyl bromides in this case. And where the alkyl chain varies depending on what we actually want on the molecule. So we vary the alkyl chain, or they varied, I keep saying we, they vary the alkyl chain such that the number of carbons was either 2 or 3 or 4. So this then gives us a Bach-protected version of what we saw earlier with now also a nitrogen group here. So this is actually, it would be an amide group here at the end, which is protected by a Bach group. Now, since that's protected by a Bach group and we don't necessarily want it to be, what we did, or what they did, was they reacted this with trifluoroacetic acid to deprotect it, leaving us with just an amine group here. Then, this amine group was reacted with, or this molecule was reacted with acrylic acid with EDCl and HOBT to promote this sort of this amide formation. This promotes amide formation, and this is sort of a peptide synthesis coaxer. And this was done in DMF and dichloromethane solution to give this molecule right here, which, as we'll see when we talk about the polarity probe, is very important. So, as for the polarity probe, I'm going to show that in the PowerPoint because it's really big and complicated and I didn't want to draw it. Gotta wait for this. So each of these derivatives is important, and all of the spectral characteristics were determined independently, but this molecule right here was actually used in the later polymer formation reactions. So it's like the star child of all the derivatives. So, I don't know if anyone can see it yet. Okay. So in order to actually get the polymer, what they did was they took this molecule, which I showed you how that was synthesized, and they reacted it with these molecules, which were basically the cross linkers for the polymer. So this resulting polymer then is a poly N-isopropyl acrylamide polymer with this added dye as a cross linker. So this is actually what they, this is actually the structure of the polymer. So you just imagine this unit repeated. So sort of like this, I don't know if this is actually exactly the monomer, but some variation of this at least repeated a bunch of times. And this was done with tetramethylethylene diamine, potassium persulfate in a 2/3 DMF water solution at 4 degrees Celsius. Now we can actually finally discuss some of the spectral characteristics. First with the absorption spectra. So what this table is tabulating are a series of absorption maxima in various solvents. Now, these solvents are arranged in increasing order of polarity as evidenced by their increasing dielectric constants, which are given here in parentheses. And a dielectric constant can be a measure of something's polarity. And the trend that we need to notice here, and what's important, is that in almost every case, the wavelength of the absorption is decreasing. And when the wavelength of an absorption decreases with increasing solvent polarity, that's called a hypsochromic shift. And that's true in each of these cases except for DMSO, which is weird. But it's still sort of an overwhelming trend. We also want to point out that just the fact that these measurements were successful in cyclohexane and benzene, we can say that confidently that we were actually able to improve the solubility, at least of the first derivative. And the reason that's true is because ABIP previously was only soluble in DMSO. So the fact that these measurements were able to be made in these solvents means that the solubility is better, at least for organic solvents. So we want to explain this hypsochromic shift, obviously, and the way the researchers approached this was first with computational chemistry. So what they did, their initial steps, were to calculate the dipoles of molecules 1 and 6. And they did this with the AM1 computational chemistry method. And they found that the dipole of molecule 1 was 0.515, and the dipole of 6, which is on your handout, and is a partially polarized structure that is a component of the larger molecule 1, that dipole was found to be 3.55. Now, what this means is this molecule 1 contains partially polarized structures. And it was reasoned that, by the researchers, that perhaps these partially polarized structures are acting as individual units that are interacting with a solvent, a polarized solvent. And that's sort of a qualitative discussion, so what they did then was some more computational chemistry to find out whether or not these structures were being stabilized in polar solvents. And these were the values that they were interested in. So here I have solvents in order of polarity as we go down, in order of increasing polarity as we move down the table, as evidenced by these increasing dielectric constants. And they calculated the molar enthalpy of formation, which we see as solvent polarity increases, this goes down, which means that it was being stabilized. And they also wanted to calculate the energy of the HOMO and the LUMO for each of these solvents. And what they found was that, so if you imagine your HOMO and your LUMO, what was happening was both were being stabilized, both were going down, but the LUMO, or the HOMO, was going down much more, or more. And so the resulting gap then is bigger, and more energy is required to evoke transitions between these two levels, and so the shift we would see in the absorption spectrum would be hypsochromic, because we know that a shorter wavelength means a higher energy, and that's what they were seeing. And they also have this handy calculation, which is just this minus this, to show us that that gap is in fact increasing. Now this is another perspective on the matter, and what we see here are molecule 1 here in benzene in red, and then in DMSO. And we see again that same hypsochromic shift. We begin here at a higher wavelength, and then we kind of move down and to the left here to a shorter wavelength. And when we have the same solvent, as is in the case with 2, we don't see any shift. Now, it's also interesting because what we can see is that as the solvent polarity increases, we see a decrease in fine structure, meaning that this peak is much more bland than this peak. It looks much more like just one peak. And that's interesting, and I'll explain that later. But the question that the researchers wanted to know was whether or not this molecule, or these molecules, were absorbing as one unit, or whether or not smaller structures within that molecule were actually doing the absorption. That's for economic purposes, that is important, because they don't want to synthesize a whole bunch of structures on a die that they don't need. So what they did then was they took these molecules, which, if you'll notice, are essentially just components or chunks of their larger molecule. And what they did was they found the absorption maxima of these two molecules independently and compared it to the absorption of the entire die. And what they found, thankfully for them, was that these two had absorption maxima, if you can call that a maximum, at very different regions of the visible spectrum than their die, which was the whole molecule. And what they conclude from this was that, yes, their die was absorbing as one unit, and that one unit would be called a chromophore, because regions of a molecule that can actually fluoresce and absorb are called chromophores. So it's not just one chromophore of their large molecule that is doing the actual absorption and emission, it's their whole die. So having adequately explained, or having explained the absorption characteristics, we can now move on to what they saw in the emission spectrum. And here I have another table kind of tabulating some of the results. This is solvents arranged in increasing polarity as you go down. This lambda represents the emission or the fluorescence maximum or maxima for these various solvents. And this capital phi, it's phi, right? I think it's phi. That is the quantum yield. And quantum yield is the ratio of the photons emitted to the photons absorbed. And it doesn't appear that there is a definite relationship between this value and the dielectric constant of the solvent, although it is nice to point out that these are really high, which is really good for them. They want to have a very efficient light-emitting molecule. We can notice a trend, however, in these red numbers, which indicates that as the dielectric constant of the solvent increases, so too does the fluorescence maximum wavelength. And what this is called is a bathochromic shift, as opposed to a hypsochromic shift. And I also only chose molecules 1 and 4 just for practical reasons because the table was getting way too big. So this, again, is another perspective on the matter. This, although notice now these units have changed to intensity because this is actually the emission spectrum, not the absorption spectrum. And what we noticed right away, aside from the bathochromic shift, so last time we were going the other direction, this time we're going towards a higher wavelength, so purple being very nonpolar and the black being the most polar, we see a continuous shift in that direction. We also notice that there's a whole lot of fine structure going on here. These are very specific peaks within each that are attributable to one singular molecule. And we also notice that it drops off really, really fast. So we have like a really sort of just blob-like peak right here. But since that image was not as clear as it could be, and since each solvent was causing sort of not as easily predictable changes in relationship between the fluorescence maximum and the solvent polarity, they made their own solvent system, which was a methanol and water solvent system. And these are the resulting emission maxima for the system, where the black line represents no methanol or no water. So this is 0% water, the most polar that system could be, and the red line represents the all are 75% water. So actually the percentages as you go are 0% water, 25% water, 50% water, 65% water, 70, and then 75% water. So they're steadily increasing the polarity of their system to get a more definite relationship and to neglect the influence of particular solvents, which all interact differently and can interact differently. So this is just a more controlled experiment. And as you can see, there's definitely some clear relationship here. The researchers just wanted to know exactly what it was, so they saw an actual mathematical relationship. And this is how they did it. They plotted the fluorescent maxima, and this is now in units of wave number, which is why this number is kind of wacky, versus the dielectric constant of that water methanol system. And what they found was it varied linearly, which is nice because they could just fit an equation of a line to that data. And now this is a relationship that describes spectral characteristics, or can relate the spectral characteristics to the polarity, which is exactly what you want for a polarity probe. You want to be able to accurately measure this and to get this. So now the researchers have a relationship. So they decided then that this a molecule in particular would be a good candidate for their polarity probe experiments. Now, before I actually show you how it's a good candidate, I want to explain the bathochromic and the hypsochromic shift. So what we need to do in order to understand this, or what we need to understand in order to understand the shifts, is that there are geometric differences between the ground and excited states of a molecule. And it is often true that the excited state has a more polar geometry than the ground state. And what this means is that excited state might interact more strongly with a polar solvent. In that sense, these solvents were varying in polarity, that would obviously be important. So the way we can visualize this, or one of the ways we can visualize this, is with one of these diagrams, which I showed you a while ago. So this being the energy of the system, and these being the nuclear coordinates. And what we need to understand, and these distributions here just represent the population, the vibrational population of the molecule. So what we need to do in order to understand how this is relevant is realize that when the geometry changes, so too do the nuclear coordinates of that molecule. And what happens then is, if this is the excited state and this is actually undergoing the geometric change, this potential energy well right here is going to shift horizontally, depending on the degree of interaction with the solvent. So if you imagine this entire potential energy well shifting to the right, then the resulting absorption is going to have to be at an increasingly higher wavelength, because the absorptions will then continuously populate higher and higher vibrational energy levels within the excited electronic level. Then, after vibrational relaxation, we come to populate this, probably, then the resulting emission will deposit, I suppose you could say, electrons onto this side of the potential energy well of the ground state, which, as you see, will be at a higher and higher energy vibrational level, which means that this green line is going to get shorter and shorter, and this blue line is going to get longer and longer. So the energy in the absorption spectrum, which is represented by this energy, or the energy required to bring about this change, is going to get bigger and bigger, which means we're going to be hypsochromically shifted. Whereas this line is going to get smaller and smaller, which is a balochromic shift. You can also use this kind of diagram to explain the spectral broadening, because if you imagine a solvation sphere around these dyes, at any given instant, the arrangement of the solvent molecules is going to be different. And as it is different, it's going to have a different effect on this potential energy well. So if you imagine the solvent molecules are all arranged in such a way that our potential energy well is way over here, then we're going to get the emission from that excited electronic state is going to populate these higher energy vibrational states. Other than if you imagine in the next instant the solvent molecules have arranged themselves in such a way that our well is over here, we're going to have a much larger energy emission. And so what that means for the emission spectrum then is it has to represent a variety of these vibrational transitions, and so we get a wider peak. It's not as defined. And that's what we saw in the why that vibrational fine structure was so wacky in the first emission spectrum I showed you. When it was a really nonpolar solvent, it didn't interact very much, and so we saw very precise transitions between vibrational levels between these two. As the solvent polarity increased, the degree of interaction increased, and we saw a much broader distribution because the arrangement of the molecules was so much more important. Now, we can get back to this. And so they wanted to, as that was much more of a qualitative discussion, they wanted to actually calculate what was happening. And so they used some computational chemistry. And what they used was a simplified model, molecule 7, I hope I wrote on your sheet, which just has ethyl groups instead of butyl groups. So it's molecule 1 with ethyl groups instead of butyl groups. And the reason they do that is because it's essentially going to tell the same story. It's just going to take a lot less time with the actual computations or the calculations. So the values that they calculated were, they simulated first a variety of dielectric constants, each representing a solvent in increasing polarity as you go down. And they calculated the dipole moment of the excited electronic state, or the dipole moment of the geometry of the excited electronic state. And what they saw was, with increasing polarity of the solvent, we also saw an increase in the dipole moment of the excited state, which means that the polarity of the excited state is increasing with the polarity of this. They also calculated the ground electronic energy. So this is the Frank-Condon ground electronic state energy, and this is the energy of the first excited state. Now, what they found with this was that, as you can see here, and as you can see from these differences, the gap was getting smaller. But it was getting smaller in such a way that the LUMO was actually being lowered, and the HOMO was going up a little bit. So this gap was kind of squishing like this, which means that the energy of the emissions is getting smaller. There's less energy required, and so the shift should be balochromic. Now this sort of seems like a competing explanation from what I just said, because I just explained that it was actually a shift in the horizontal shift of the electronic state in that diagram. But what's likely true is that it's a combination of these effects, not just one. They're not mutually exclusive explanations. probably contributions from both, especially in terms of the solvation interactions. Now I can talk about finally how this was used as a polarity probe. So a polarity probe, firstly we need to understand, the purpose of a polarity probe is to measure polarity, measure polarity inadvertently by measuring some other characteristic. And since we're talking about dyes, and I just showed you a bunch of stuff with absorption and emission spectra, we're obviously going to use the spectral characteristics of that dye in order to predict the polarity. And from what I've been describing, how these spectral characteristics have been changing the polarity of the environment, this is a solvatochromic dye, and because this is essentially exactly the definition of solvatochromism, which is I've already given. Now, the way they actually went about doing this, I showed you the structure of the polymer they used, which was a polyanisopropyl acrylamide gel, or a polymer, but the way it actually existed in these experiments was as a hydrogel. And so the reason they chose that is because if you imagine a hydrogel in its swollen state, it's going to have a whole bunch of water surrounding the dye that is embedded in the polymer. Then, as you increase the temperature, eventually you'll reach a volume phase transition temperature for this hydrogel in particular, that's at 34 degrees Celsius. Upon that volume phase transition, all of the water will leave the hydrogel, and you'll be left with your polymer and water, two distinct phases. And what that means then is the polarity around that dye that is embedded in the backbone is going to be different, which is going to evoke a spectral change, which can be measured. And if you can measure those, we know you can find the polarity via the relationship they determined earlier. And this is what they found. They found it did exactly that. These are the fluorescence maxima versus temperature, and the inlay is just an emission spectrum. So what they found was that at 23 degrees Celsius, which is well before the volume phase transition temperature, the fluorescence maxima was 442 here. As they approach the volume phase transition, we see this hypsochromic shift until we reach the volume phase transition, at which case it plummets way down. So this is, if you can imagine, this is the expulsion of the water from the hydrogel. Then down here, we pewter off, and eventually at 38 degrees Celsius, well above the volume phase transition temperature, we have a wave or emission wavelength maximum of 433 nanometers. And this is exactly what we should expect, because when we saw in the emission spectrum that a bathochromic shift was brought about by increasing the solvent polarity, if we decrease the polarity around the probe, we should expect the opposite, which would be a hypsochromic shift. And this is just really another way of looking at it. We have A before the volume phase transition, and B, which represents after the volume phase transition, which is a hypsochromic shift. Now what's neat is they actually use the relationship they had determined earlier in order to calculate the polarity of around the backbone, around the dye in the backbone before and after this transition. And what they saw was that the polarity at 23 degrees Celsius, so up here, was 60, and then after the volume phase transition, it went down to 33. So the polarity is decreasing, the relationship is working, so that's obviously good for them, and they successfully made this into a probe. So now to revisit all of the concepts that I've introduced, they set out to improve the solubility of their dyes, which based on the fact that they were actually able to make these measurements in the first place in non-polar solvents is evidence of that. They wanted to investigate and define the absorption and emission properties, and we did that. We saw that there was a hypsochromic shift in the absorption spectrum and a corresponding bathochromic shift in the emission spectrum, and we explained those. Then we wanted to use this as a polarity probe, which, given the relationship and its ability to sensibly predict polarities around the dye, that was labeled a success. So I would like to thank you for listening, and I would ask you now if there are any questions.
I have a bunch of questions.
Go for it.
First of all, from an organic chemistry point of view, looking at your, well, really any of your molecules before you polymerize them, it seems to me there's two possible rotational states, if you will. So that molecule up there, for example, is kind of trans,
Right.
in that your two side chains are pointing in opposite directions. Is there any indication that, because the thing is flat, I guess it would exist like this, or possibly in a cis-type state. Do you know what I'm talking about? Where the,
So you mean just BBIP, right? Or are you
yes.
talking about one of these?
Well,
Okay.
any of them
Okay.
where you have the long chains.
Right. Well, the reason they can't do that is because these atoms can't rotate. So they've got these perpendicular pi orbitals, and that energetically is so favorable that they're not going to rotate out of that plane to reduce the overlap between them.
Right, but they could, but what that means is that theoretically they could exist in two isomers.
Oh, I see.
You could have the cis-type isomer and the trans-type isomer.
Yeah.
And you've drawn the trans one, and I'm assuming that's way more stable, but was there any indication that ever they form a cis-type, cis-type molecule?
Yeah, I don't know. They didn't mention it.
Yeah.
And I guess it would be possible.
Because, and the reason I'm asking that is
Maybe they
because
isolated this. I don't know.
it seems to me that when you have them in the transoid type arrangement, there should not be polar at all. It should have zero polarity
Right.
because it's symmetrical.
Yes, and the dipoles will cancel in every
Right.
direction.
And yet you showed on one of your slides that it does have some polarity.
0.51.
Yeah.
That was the divide, yeah.
Any
That could-
idea why?
It might be that like there's some sort of like, it wouldn't be like a full twisting effect, but you can kind of like imagine, or at least I can imagine, I don't know if it's right, but I can imagine the molecule has like sort of like a jittering, where it's like sort of constantly vibrating, and the nitrogen, so if these are like your NH groups here, at some instant they might be a little bit torqued like that,
Right.
and then a little torqued like that, and so forth. And so it could like, at any given point where that's uneven, it would actually have a dipole.
Right.
So
So
that's-
in the state where it's absolutely flat, it would be nonpolar, but it's
Absolutely
possibly
nonpolar.
that it could.
Yeah, so if it's torquing like this continuously, it would have just a tiny dipole. which
Yep.
would be something. That's what I would think of.
Makes sense to me. I have some other questions too, but I'll let other people ask them.
Just curious, you mentioned they used trifluoroacetic acid in one of the reactions. Why do they choose that as opposed to acetic
Because,
acid?
well, I imagine it's a much stronger acid than, well, it is stronger than acetic acid because of the electron withdrawing effects of fluorine.
Right.
So it's gonna make that, it's probably just the right pKa for their reaction, probably not too strong, probably not too weak.
Okay.
And it might be because of the resulting conjugate base too, they would want to control that. And so, but it is stronger than just acetic acid.
And you had another slide in the polymerization process.
Yes.
Couldn't get it out. There are lots of functional groups in there. Okay. So what determined how this was going to polymerize?
It was important to have, if you notice, this group, because this had to be, what happens was that double bond sort of comes apart and links with all of the other double bonds. So it has to have something with this on the end so that it can make that kind of like track down the side. So that's what's actually really important. And then what you have to have, let me go back to that slide, where it actually shows. Just you and I. So you notice that everywhere where it connects, it's got this double bond here.
Okay.
And that's necessary. And it probably helps that this is also an electron withdrawing group to make that happen a little bit more easily, maybe.
Yeah, because the reason I ask is you've got aminos and carbonyls and all kinds of other things in there, so.
But you'll notice that that group that Travis mentioned, that 2-carbon group with a double bond, that's essentially a quote vinyl group.
Yeah.
Right.
Quote. And so this polymer is very much like polyvinyl chloride, for example, or any other
PDA,
vinyl.
right, yeah.
Yeah. So it's what's called an addition polymer, where you're just zipping it up, you're not substituting it. Whereas any other polymers that could form would be substitution polymers.
Right. No, that's the answer I was looking for. Travis.
Okay.
Sorry.
Very good, very good.
Sorry, I jumped on that.
No, that's right, but no. You didn't answer the question, yes.
Okay.
Okay.
Anybody else? Go ahead, Dr.
Okay.
I know.
I was a little confused on your slide that showed the straight line relationships, where you actually had 2 straight lines.
Yes. So that was for the 2 molecules. So the closed circle is this one, and the open square is this molecule.
Oh, okay, so
With the
4A and 4B are referring to, okay,
actual different molecule.
gotcha. So there's a slightly different slope
Yeah, and you also see that in the absorption spectrum. Each of the alkyl change actually changes the spectral characteristics a little bit. It's, at least in the absorption spectrum, you could probably explain it just by saying they have different molar absorptivities because they're different molecules. And I'm not entirely sure how having an alkyl chain is going to, I don't remember whether it went up or down, but I'm not sure how that's affecting that, but since this is basically related to the absorption spectrum in that it is the corresponding emission spectrum, I'd imagine there's some sort of explanation about why those alkyl chains are causing that. So
It's just a slightly longer alkyl chain.
yeah,
So that would mean in the polymer, it's
wider.
a slightly wider polymer, yeah. More water in the hydrogen.
Maybe.
But that brings me to my next question, which was,
That's interesting.
when you were discussing the hydrogel and the phase transition,
Yeah.
can you put that slide back up?
Volume phase.
That one,
That one.
right there. Okay. I'm a little confused what we're actually measuring the polarity of.
We're measuring the polarity of the environment around the backbone of the polymer. So it's an inadvertent way of measuring polarity in that you look at the spectral characteristics that are brought about by the polarity. So you're measuring it's not really the polarity of the molecule, it's the polar environment around the molecule.
But that's water, isn't it?
Yeah, but it's as measured by the effect water has on the molecule. So you're measuring the polarity sort of an interaction, more so. It's how I sort of understood it to be.
Well, basically the hydrogel is bathing these probe molecules in water.
Yes.
And so,
The water's trapped sort of in the strands of the
right, so really what you're measuring is the polarity of water, isn't it? Or is the idea that you could use other solvents and therefore somehow measure the polarity of other solvents using the same kind of a system, and they're just using
Yes,
water
I
as
think
a...
if you use, I think the relationship that they got was relating polarity to fluorescence emission wavelength, and that wouldn't matter whether or not you're using water at all, because the relationship is linear. So you know that the fluorescence maximum is varying linearly with polarity, and polarity is just, it's particular to each molecule, but it itself, there's a definite relationship that excludes needing to know what the actual molecule is. Because polarity itself isn't something that is unique to any one molecule. Well, it is actually unique to one molecule. I don't want to say it's an intensive property, but it's, what you can do is if you know it for one system in which you're defining two things that are not dependent on the molecule, then you can measure it for any other system, is what I'm saying. Which
Did they think about to what lengths of polarity that would remain linear, or did they only see it in that small piece?
they only saw it, well, and actually, so the difference between just methanol and just water is actually probably pretty big. So I mean, that difference that they measured was probably sufficient for most cases, at least when they would want to use this. So their range was pretty good, actually.
I've got a couple questions on some of the computational stuff.
Okay.
Could you go to the AM11 chart?
This one is, So this is
Next
where I
one, the
introduced-
next one.
which one, what was it calculated?
Where you did the AM1 method with the, there.
There.
No, not that
No.
one. There's one more later.
I think it was.
There was one where you had the energies.
We did AM1 there.
Not that one. There was one where you had the
Yeah.
ground state and excited state.
This one.
Yeah. Couple questions. First, did they talk about how do you get solvents into the calculation?
It's not, well, because they can't actually replicate solid molecules around the dye in their computation. That would be way too much computer time required. So they can't actually have a solvation cell and as we know, that changes way too much from time to time to actually do a computation with it. So what they do is they just have like a field basically that the molecule's in that is represented by that dielectric. That's what I understood the explanation to be.
So how does that dielectric affect the calculation?
It's kind of like an a priori state for the calculation to take place in. So you define the environment and then you do the calculation with the molecule in the environment and see how it differs from just with no dielectric.
Right. What do they change? Do you know what they change?
I'd imagine,
The calculation?
so the definition of just like a dielectric is just something that concentrates electric field lines. So I'd imagine if what they would do practically, like what they would do, how they would actually do the calculation, is total speculation, I have no idea. But the way they would do it would be they would just have that field present in the space where they did the calculation.
And they would represent
Like a point
that
charge
by
that
guess.
looks like,
What I'm thinking is, my guess is they would represent that by changing the potentials that they're using for the calculations. Because there's always a potential field that gets involved in a calculation.
Okay, that makes sense.
My guess, I don't know.
Yeah, I don't know either.
Do you know what the S's represent? The S zero and the S
Singlet
one?
states.
Okay.
So it has to be the same, it has to remain a singlet state from the selection rules of electronic transition.
Speaking of selection rules, you go back to the ones showing the potential curves?
Back or forward?
Either, because you did one at the beginning and you did one there somewhere.
That's too far. Gotta be back.
There, no. How does selection rules apply in here?
Well, so the process of vibrational relaxation, this is actually interesting because, for instance, you might think that if the difference between the transitions within these states, so for instance, imagine that an electron is fluoresced down to level 6. And perhaps then it could fluoresce all the way back down to level 1 within that, and you might be able to see that energy. But the selection rules for vibrational states is that you can only go to adjacent states. And so the energy of fluorescence between them is invisible, the energy is too small. So you can, however, boost an electron from here, I think, into any of these.
So that's essentially what I'm getting at. Does the plus or minus 1 selection rule, is that within a state, or does that
That only
count
applies,
within separate states?
I think it only applies, so for instance, that applies for this electronic state. The vibrational selection rule, which is just plus or minus 1, so we do adjacent ones, that would be for this one. So for instance, an electron here would go here, but not like there. But for this, it could go anywhere in here, right?
I think it has to if what you're saying is correct, because otherwise, the whole point of your energy shifts was that you're going to different levels. And if they weren't allowed to go to different levels, they would still have to fall to the same place. Does that make sense?
I think.
But that would be interesting to think about, because I know that usually isn't discussed.
Yeah.
You're right, usually the discussion is just within a single.
Yeah. State, but whether or not we can
Electronic
actually
state.
go to different vibrational that defy that rule. So for instance, from 0, could it go to 3, or would it have to go to 1? But it couldn't really, because it has to go higher, so.
Because the geometry doesn't match.
Right, so it's completely dependent on the nuclear coordinates.
Travis, an easy explanation, I think, is if you change polarity, you have shifted to the right.
Yeah, so it has to go into
Automatically
higher
it goes to a different
Yeah.
level.
But the rules say it can only change to a vibrational level plus or minus 1.
So that has to only apply then.
So
to
it can't
this
go from
one
0
state.
to 4. It has to go from 0
Even
to
if you
1.
change polarity?
That's the question.
Yeah. So that can't be true then. It has to be able to go into different vibrational states within the excited state, so that can only apply then to states within one electronic state. That would have to be true, I think.
I would think, but I don't know.
Travis, I'm gonna ask a really easy question, because that's what I like to ask. You use the word red shift.
Yes.
What does that mean?
It means you're shifting to a longer wavelength.
Okay, why do you use the word red?
Say that again?
Why the word red?
Because it's approaching the red end of the visible spectrum. So you can think of like the Doppler effect or like galaxies being red shifted. They appear red because the wavelength is longer between them.
Two other quick questions. There was one peak where you showed the cyclohexane as a bimodal emission curve. Did they address that at all?
The cyclohexane.
I think it was cyclohexane. You were going pretty quickly for me to get notes on.
Sorry.
There was one spectral curve of emissions
Oh, well, let me just try.
That was it,
Oh.
back, right there. Cyclohexane was in purple. That's the fluorescent spectrum.
This
Yeah.
is purple.
Did they address that bimodal? I was the only one I ever saw that was truly a bimodal.
They didn't, but it has to mean, if you think about it, it has to mean that there's two really probable transitions between the ground vibration electronic state to two really probable vibrational states within the excited state, because the transition is happening, the subsequent emission is happening from, so if you imagine, so keep that in mind. So if we imagine this, it's happening between, the emission is happening such that the energy of them is really consistent. So for instance, like 4 to here and 2 to here. And it's staying between those two states fairly consistently. The reason being, cyclohexane isn't going to interact very much with the dye, and it's not going to have very much solvent interaction. So if the solvation sphere changes around it, it's not going to matter, because it's not interacting with it anyway.
Go back to your slide where you had phi, as you call it phi.
Oh,
That capital phi. There you go. Okay.
sorry.
Notice the difference between cyclohexane and all the rest of them.
Well, too, if you go back to the slide where you had the one he was just referring to, where you had the 2 peaks in the purple line, all the other colors also have 2 peaks.
They're just not, yeah.
It's just they're closer together, and so
Right.
they overlap.
Right.
So it's not really just bimodal with cyclohexane.
There's a
It's
shoulder
just,
peak in all of them.
Yeah.
It's just-
actually, there's 3 of them,
Yeah, for this one.
because there's a shoulder on the
Right,
purple one
right,
as well.
right, yeah.
So there's 3 significantly probable transitions.
Right. And it's true with the other ones, it's just they're closer together so that they overlap more.
Functionality.
When we talk about the shifting, it'll shift different amounts
Yes,
based on.
based on the solvent interaction.
And
Yeah.
one other simple question. Did the researchers consider using anything other than organic solvents, like a biological solvent? Because you're not going to find these in a biological system. These are organic.
Yeah, that's
systems.
if they did, they didn't publish those findings, and I didn't read them.
Okay, just
So-
What would be a biological solvent, just out of curiosity?
well, starting with water and
Well,
then.
Well, they did do water, they did it mixed with
I
methanol.
understand, but water by itself is not truly a biological system either.
Oh.
You know,
Oh,
it just
so you mean,
lives in water.
you mean
There's
Like some sort of
a more
dissolved
complicated solvent
salt.
system, yeah.
like a phosphate buffer.
About that. I don't think that they did. I think they
Or
probably
just
said
adding
that.
sodium chloride to a water and just then see what happens.
They didn't do that, and I'm not sure exactly what would happen.
Based on that slide right there, what do you think might happen? None of those solvents are exactly what you call polar, but methanol is polar, acetonitrile is polar.
DMSO is quite polar.
That polar, okay, so, yeah, what?
So if you added, so for instance, like salt to water, I'm trying to think of what that would actually do to the polarity of the water.
Yeah, does it make it more polar or less? That's a good question.
See, I'm not sure.
Well-
If you think about how the ions would interact with the water, though,
Yeah.
you'd have like a positive sodium sort of interacting with the negative oxygen. And I'm not sure if that would make the hydrogens more protic, and that would interact more strongly, which would shift it that way, or whether the opposite would be true, and the hydrogens would be kind of crowded over by the chlorides.
Well, that might be why they use the hydrogel thing, and you can measure very quickly how does that shift with when you add salt to it. That would be a perfect way of using this system. I have one more thing. I know we need to go, but very simple question. When you were originally explaining about what fluorescence is in the first place, you know, the
Yes.
shift and all that kind of stuff, does that happen with all molecules and we just don't see it, or does it
So-
only happen with certain molecules?
It only happens, so for instance, a lot of organic molecules, the energy required to cause the transition of electrons from the sigma bonding orbital to the sigma star, or the anti-bonding orbital. The transition will happen unless there's sufficiently high energy around. So for instance, in just sunlight, I'm not sure exactly what the highest energy photons in sunlight would be, but that transition will not occur unless it's exposed to energy that can evoke that transition.
But could we use X-rays or something and,
Then it could happen, yeah.
Yeah.
We wouldn't be able to see it because
Right.
there's no way that vibrational relaxation would bring the energy down enough to see it, but that happens.
so fluorescence may be happening with all sorts of molecules, it's just we don't really
We
notice
can't
it.
see it.
Yeah.
Yes.